Наверное, это не играет, но так непонятно его включать. Okay, at the end of the previous lecture, we began to discuss locally compact groups. And we introduced the notion of a uniformly continuous function or topological group. So let's recall the definition. Suppose that G is a topological group. We say that the function f on G is, and here we have two options, the left and the right, uniform continuity. We say that f is the left, respectively right, uniformly continuous. Uniformly continuous. If for every positive epsilon there is a neighborhood of the identity U, such that for all elements x in G, and for all elements little u in its neighborhood, we have the following inequality. F of x minus f of xu is less than epsilon. This is for the left uniform continuity, and respectively for the right uniform continuity, you have the following: f of x minus f of xu is less than epsilon. Or equivalently, this can be written as follows: f is left, respectively right, uniformly continuous if for every positive epsilon there is a neighborhood U of the identity such that we have a f of x minus f of y is less than epsilon whenever the element x inverse y sits in U. This is the left uniform continuity, and for the right we have the condition that yx inverse belongs to U.
I'm sorry, what is the difference between the second line and the third line, like in the definition?
There is all the things, thank you. F of ux, thank you. The right uniform continuity is we use right translates of u of our neighborhood. So we must write yx here. Thank you. And I hope this corresponds to this one. Yes. So if y is yx, then yx inverse is ux times x inverse. That is exactly little u, which sits in our neighborhood. Okay, so this is formal definition. Clearly, if our group G is just the real line, then we come back to the usual definition of uniformly continuous function in the sense of the standard calculus course. So our first little goal for today will be to show that every continuous compactly supported function on a locally compact group is left and right uniformly continuous. Suppose that G is a locally compact group and F is a continuous compactly supported function. So let's recall that this notation means that we consider all continuous functions with a compact support. So I claim that F is left and right uniformly continuous. We will need a simple lemma from general topology. The lemma is very simple, but it's very useful. Suppose we have topological spaces, x, y, and z, topological spaces, and a continuous map f, big F, from x cross y to z. This is a continuous map. Also, let's choose an open subset in z, z0. This is open, and a compact subset denoted by y0 in y. Compact. And let's consider the following set x0, which consists of those points x in x, such that f of xy belongs to z0 for every y in y0. I claim that this set is open. x0 is open. So what's the meaning of this lemma? Well, clearly this set is open if y0 consists of a single point. If y0 consists of a single point, then this is just the preimage of the open set z0, which is also open. For the same reason, this set is open if y0 is finite. In this case, this will be open because it is the intersection of finitely many open sets. So roughly, our statement states that the intersection of a compact family of open sets is open. And the proof is quite elementary. This is a good exercise in general topology. Let's now prove our proposition. First of all, let's observe that a function f is left uniformly continuous if and only if the function sf, where s is the usual antipode map, is right uniformly continuous. And the other way around. Here sf of x is f evaluated at x inverse. This is clear from the definition. So we see that it suffices to prove that f is left uniformly continuous. Let's show that f is left uniformly continuous. So this compact is supported. So let big F denote the support of F. And let's choose a relatively compact symmetric neighborhood of the identity. A relatively compact, which means that the closure of U is compact. A symmetric neighborhood of the identity. Let's recall that symmetric means that V inverse equals V. And in the previous lecture, we observed that every neighborhood of the identity contains a symmetric neighborhood of the identity. And let's also denote by K the following set. This will be the product of F and V, closure of V. So F is compact, the closure of V is compact, the multiplication is continuous, and the continuous image of a compact set is also compact. So we deduce that K is compact. K is compact. Let's now choose a positive number epsilon. And let's introduce the following set. Let's denote it by W. W consists of those points y in our group, such that for every x in K, we have the following inequality. F of x minus f of xy is less than epsilon. So what can we say about the set? We can apply our lemma. So clearly, what is written down here depends continuously on x and y. So this is a continuous function on the product of G by itself. We have the privilege of an open neighborhood of zero. So we apply our lemma and deduce that that W is open. W is open. And it's also clear that it contains the identity. And let's now take the intersection of V and W. Let U denote the intersection of V and W. So this is a neighborhood of the identity. And I claim that this neighborhood satisfies our condition of uniform continuity. So we have to show that that we have this inequality, or equivalently this inequality, whenever little u sits in our neighborhood. Okay.
So why is K compact?
K is compact because, well, F is compact. The closure of V is also compact just by construction, and the multiplication is a continuous map.
Yeah.
So the continuous image of a compact set is compact. First of all, if x belongs to K and y belongs to U, then we obviously have the following inequality.
Sir, may I have the question?
Yes, sure.
For which map do we apply the lemma here? Like,
The map is f of x, y is f of x minus f of x, y.
oh, okay, so
And y0 is the epsilon neighborhood of 0 on the real line.
okay. Thanks.
Okay, so if x is in K and y is in U, then this is clearly less than epsilon, just by construction, because y is in U, so it is in W. And just by the definition of W, we have this inequality. Let's now suppose that x is not in K. So x is a point in G which is not in K, and y is still in U. Then, of course, f of x is 0. F of x is 0 because it is not in K. And moreover, it is not in F. F is smaller than K, but F is the support of little f. So x is not in the support, and f of x is 0. And I claim that f of xy is also 0. If we prove that f of xy is 0, then we are done, because in this case, both terms here are 0. So if not, let's assume the converse, suppose this is not 0. If not, then then xy belongs to f, of course, to the support of our function, which implies that x belongs to f times y inverse. But y sits in U. So in particular, y sits in V. V is symmetric, so y inverse also sits in V. So we are in f times V, which is contained in K. And we get a contradiction, because we assumed that x is not in K, and finally we obtain that it is in K. So this is contradiction. Yeah, this contradiction completes the proof, because we now see that f of xy is 0, and so this inequality holds for every x in G. Well, let me write this down. So this implies that f of x minus f of xy is less than epsilon for all x in G, and for all y in U. And this completes the proof. So we get the left uniform continuity for little f. Okay, this is a very useful result. It's quite technical, but we'll use it many times in our course. And now let's turn to the Haar measure on locally compact groups. The Haar measure. Well, this is one of the main ingredients of harmonic analysis. Suppose that G is a locally compact group, and mu is a random measure on G. As before, we always assume that all our random measures are positive, but not necessarily finite. And we say that mu is left invariant, respectively right invariant, if it is invariant under left translations or respectively under right translations. If for every x in G and for every Borel set B in G, the measure of xb equals the measure of b. This is the left invariance property, and respectively the right invariance property looks as follows. Of course, we always have a trivial example, that is the measure which is identically zero. It is both left and right invariant. This is not very interesting. The interesting case is the case where mu is not identically zero. And in this case, if moreover mu is non-zero, then we say that mu is a left respectively right Haar measure. Haar measure on G. So such a measure is named after Alfred Haar, who was he was a PhD student of Hilbert, and he proved the existence of such a measure in an important special case. First of all, by looking at this definition, we can easily observe that there is a simple one-to-one correspondence between left and right invariant measures. Then let's observe that if mu is left invariant, then mu of b, which is defined in the following way, is right invariant. Yeah, the other way around. So there is a one-to-one correspondence between left invariant measures and right invariant measures. So because of this, we will adopt the following standard convention. When we say just a Haar measure, we always mean a left Haar measure. Let's look at some of those examples. First of all, clearly the counting measure on a discrete group is both left and right Haar measure. The counting measure on a discrete group. Clearly, it is both left and right invariant. And what if G is not discrete? Well, it's still left and right invariant. But it is not a double measure, because, well, try to understand why it is not a random measure. The measure of a compact set is required to be finite. So if G is not discrete, then the counting measure is not a random measure. Example 2, of course, the usual Debye measure of the real line, or more generally on Rn, is left and right invariant, so it is the Hard measure. And the usual length measure on the circle if you like, we can divide it by 2 pi. Is also a Hard measure. So basically, these are the examples that we discussed in the previous lectures. Slightly more advanced examples, well, I'll give you slightly more advanced examples fairly soon. We have the following fundamental theorem due to Alfred Haar, Jonathan Neumann, and André Weil, which states that if G is a locally compact group, then there exists a Haar measure on G. And moreover, such a measure is unique up to a multiplicative constant. If mu and nu are 2 Haar measures, then there is a positive constant C such that nu equals C mu. So the Haar measure is essentially unique. The history of this result is as follows. First, Haar proved in 1933 the existence of a Haar measure under the assumption that G is second countable. A few years later, if I'm not mistaken, in 1936, von Neumann proved both the existence and the uniqueness under the assumption that G is compact. And the general case is due to André Weil. Of course, some special cases of this result were known before Haar. For example, the existence of a Haar measure on the orthogonal group and on the unitary group was known already to Schur and Hurwitz and later to Hermann Weil. This is the end of the 19th century and the beginning of the 20th century. And in the 1920s, Hermann Weil and his PhD student Fritz Petter proved the existence of such a measure on every compact real Lie group. And in fact, the argument easily extends to an arbitrary Lie group, not necessarily compact. So before proving this result in the general case, let's see how to construct a Haar measure on a Lie group. So suppose that G is a real Lie group. Let L denote the dimension of G. Let's choose a non-zero element, let's denote it by omega e, in the higher exterior power of the cotangent space at the identity. This space is one-dimensional, so we choose every non-zero element in this space. So now basically the idea is to use translations and to obtain as a result a left invariant differential form of higher degree. So formally the formal construction looks as follows. Let's, for every point in our group, consider the left multiplication Lx a left multiplication map, which acts as follows. And let's, by using this map, we can identify the tangent space at the identity and the tangent with the tangent space in an arbitrary point x. So let's consider the differential of this map, dLx, or Lx star, which acts from the tangent space at x. Oh, it's better to replace x by x inverse here, x inverse. So it acts from the tangent space at x to the tangent space at the identity. Now we take the dual map, Lx inverse star, which acts from the cotangent space at the identity to the cotangent space at x. So this is a linear map. We naturally extend it to the exterior algebra of the space. And now let omega of x denote the image of our element omega e under this map. Omega e. So this is an element in the higher exterior power of the cotangent space at x. Well, since this map depends smoothly on x, what we get is actually a differential form, omega, of higher degree. Differential form of higher degree. Moreover, it is not zero. It is not omega x is non-zero for every x. So as a byproduct, we see that, why do I write M? M is our, not M, but our group G. G. And by the way, we see that G is orientable, because we have a differential form of higher degree, which is nowhere zero. So in particular, we see that G is orientable. Let's now choose the orientation which is compatible with omega. We choose an orientation, which is, by the way, which is obviously unique, such that omega is positive. So once we have chosen an orientation, we can now integrate differential forms of higher degree. And in particular, we can integrate our form omega itself. So we can now define a measure.
Sorry, why is J orientable?
Well, one of a possible criterion for the existence of the orientation of a manifold is the existence of a differential form of higher degree, which is nowhere zero. This form is nowhere zero, so it's equivalent to the existence of the orientation. Okay, so now for every Borel set V in G, we denote by mu of B the integral of omega with respect to B. So I claim that mu is a left power measure. Mu is a power measure. Well, indeed, why is it so? First of all, by construction of omega, we see that omega is left invariant. Lx star omega equals omega for every x, just by construction. So omega is left invariant. Next, we observe that mu is indeed a random measure. Mu is a random measure. Well, indeed, it is a measure by the properties of the integral. Why is it regular? Why is it a random measure? Clearly, the measure of every compact is finite, again by the properties of the integral. And G, by assumption, we assume that G is second countable. This is a standard convention. When we speak of smooth manifolds, they are always assumed to be second countable. And we have already discussed in the previous lecture that Borel measure, which is finite, a Borel measure on a second countable locally compact space, which is finite on compact sets, is automatically inner and outer regular on all Borel sets. So it is a random measure. Now we have to show that it is left invariant. This is a simple calculation. Mu of xb is, by definition, the integral of omega over xb. By the well-known change of variable formula for differential forms, this is equal to the integral over b of Lx star of omega. And here we use the fact that Lx preserves the orientation. X is orientation preserving just by construction. So since it is orientation preserving, we have this formula. But omega is left invariant, so this is equal to the integral of omega over b. And this is mu of b. And that's it. So we deduce that mu is left invariant. So it is a left power measure in G. In some applications, it's useful to have a coordinate form of this omega, omega and mu. So let's write this down. A coordinate form of omega. Let's choose a little neighborhood of the identity, which is diffeomorphic to Rn, and let's choose global coordinates in this neighborhood. Let's denote them by y1 up to yn. Coordinates in a neighborhood of the identity. So, and we have to choose a non-zero element in the cotangent space A, the identity. The obvious choice is the following one. So now how can we calculate now omega at a different point? So let's choose P, a point P in G. We have to apply this map to omega E. So we recall that it acts on the top exterior power of the cotangent space. And the action of this map is a standard fact from calculus of manifolds that the top exterior power of this map acts as the multiplication by suitable determinant, by the determinant of the Jacobi matrix. So we deduce that omega of P is the determinant of the following linear operator, L P inverse. Well, I can put the star in the subscript because the determinant of a matrix is equal to the determinant of the transpose matrix. So I can put star here, or I can put it here. The determinant will be the same. So we calculate, take this map at P, take the determinant, and then multiply by D. Of course, in order to make sense of this formula, we have to also choose coordinates in the neighborhood of P, sorry. X1, Xn are the coordinates in a neighborhood of P. Okay, so dx1 up to dxn. Okay, or more, even more explicitly, this is the determinant of the following matrix. The matrix consists of partial derivatives, dy composed with LP inverse, dxj evaluated at P, dx1 up to dx. So this is the explicit formula for omega. So basically the formula involves the multiplication by the inverse element, P inverse. Now let's look at some concrete examples. Example 1, G is the multiplicative group cross of non-zero real numbers. So if I take P, then this map is just a multiplication by P inverse, that is the division by P. If X is now the global coordinate on R, which is just the identity map of R, then by using our formula, we see that omega of P is dx over P. A delicate point here is to introduce the orientation on R cross. The point is that the orientation on R cross compatible with omega is not exactly the standard orientation on the real line. This is the standard orientation on positive numbers and the opposite orientation on the negative numbers. Let's recall that when we constructed omega, we required that the orientation on G is compatible with omega in the sense that omega is everywhere positive. So if we want to integrate, not with respect to omega, but with respect to the usual Lebesgue measure, with respect to the usual orientation on the real line, we have to modify our formula slightly, and we come to the following formula. For every continuous compactly supported function f on the real line, the integral R cross of course. The integral of f with respect to the R measure is the integral with respect to the usual Lebesgue measure divided by the absolute value of x. In other words, mu is the Lebesgue measure divided by the absolute value of x. So this is the explicit formula for the R measure on R cross. This example can be extended to the general linear group, GLN. This is example exercise 2. Let G be the general linear group of all invertible n by n matrices. Prove that the left Haar measure is equal to the right Haar measure in this case, the group is not abelian, but the left and the right higher measures are the same. And they are given by the following formula. This is the Lebesgue measure divided by the nth power of the absolute value of the determinant. So clearly this formula generalizes this one. This corresponds to the case where m equals 1, and this is a general case. And one more exercise, example exercise 3. Let's consider the group of affine transformations of the real line. So for every two real numbers a and b, where a is non-zero, let L, A, B denote the following self-map of the real line, given by the following simple formula, ax plus b. So clearly all such transformations form a group. They form a group that's denoted by G. And we can easily make it into a Lie group by identifying this group with a group of all 2x2 matrices of the following form. So now we see that this is a Lie group, and moreover, A and B are global coordinates on this group. The exercise is to find explicitly in terms of the global coordinates, in terms of A and B, the left higher measure, mu left, and the right higher measure, by using our general formula. So we discussed this formula for the for the case of a left higher measure, but clearly a similar argument works in the case of right higher measure. We have to replace left translations by right translations here. And show in particular that these two measures are different. They are not the same. Show that they are not the same. Okay, some more concrete examples of higher measures on Lie groups will be given in our exercise sheets. And let's now turn to the existence of higher measure in the general case. So suppose that G is a locally compact group. Before constructing the higher measure, let's briefly discuss a rough idea, a rough geometric idea, which is behind the construction. We choose a neighborhood of the identity, mu, neighborhood of the identity, and for every Borel set, B in G, we define the following number, which will be denoted like this. And in some sense, this number is a relative size or a relative area of B with respect to U. So formally, this is the minimum number of M, such that such that B is covered by N translates of U. B is contained in X1 U, X and U for some points X1 to Xn in G. So clearly, finitely many translates of U cover B. If B is not compact, then this is not true. But in this case, this number is infinite. But if B is compact, then this is finite. So in some sense, this number is a relative size of B relative to U. So let's draw a picture which explains the geometric idea behind this construction. So this is U, and this is B. So the picture shows that if, this is not good because we assume that B is contained in the set. So I must draw something like a bigger set, which is the union of finitely many translates of U, but contains B. And the picture shows that if U is small enough, then this number is a good approximation to the area of B divided by the area of U, whatever this means. At least this looks like something reasonable if we are in the plane. Of course, there is a problem with this definition, because if U shrinks to the identity, and we must, to get better approximation, we must make U smaller and smaller. But if U shrinks to the identity, then this number goes to infinity. This one goes to 0, so the fraction goes to infinity. So to get something reasonable, we have to normalize this number in the following way. We choose once and for all a compact set G, K in G, with a non-empty interior. We divide the relative size of B by the relative size of K. So the role of K will be that this is sort of a reference sample, that is a fixed compact set whose measure is declared to be equal to 1. And after we consider this, we take the limit of this number as U shrinks to the identity. And we define our measure about this formula. So this is the geometric idea behind the construction of our measure.
I'm sorry, can you repeat why we divide this?
This definition is good, but if we want to get something which resembles the real area of B, we must make U smaller and smaller. But if U is getting smaller and smaller, then the area of U goes to 0. That's the idea. And this is the reason why we introduce K. So we must choose a compact whose measure will be 1 from the very beginning. This is the reason why we define, why we choose K. So this looks reasonable, but in fact, if you want to make this rigorous, there are a lot of delicate points here. First of all, we must explain in which sense we understand the limit here. This is not entirely trivial. And even harder problem is to show that the limit exists. And a much harder problem is to show that this definition indeed gives us a measure. In fact, it turns out that this procedure works well on the case where B is compact. So first we will define a measure on compact sets, and then we have to somehow to extend it to all Borel sets, which is also not entirely trivial. So a full proof which follows this idea can be found, for example, in the famous book by Paul Halmush, Measure Theory. And we will choose another approach to the Haar measure, which is due to observation. So the main idea of this approach is to replace measures by positive linear functionals on compactly supported continuous functions. So that is to use the Markov-Kakutani theorem, which gives us a bijection between random measures and positive functionals on continuous compactly supported functions. The resulting construction of the construction of a left invariant functional, of a left invariant positive functional, maybe it is geometrically it is less transparent than this idea, but technically it is much easier. Okay, so let's now try to construct a left invariant functional. Before doing this, let's introduce some notation. First of all, if mu is a random measure on G, and x is a point in G, let's define two random measures, Lx mu and Rx mu, as follows. Lx mu of B is mu of x inverse B. And similarly, Rx mu is mu of Bx, mu of Bx. So Lx mu is the left translate of mu, and Rx mu is the right translate of mu. So the role of x inverse is clear from the following identity. So we have the following easily verified equality: Lxy equals Lx and y, and similarly for Rxy, Rxy equals Rx, Ry. This is a little, well, this is not just an exercise, this is almost obvious. Okay, and well, it's clear from this construction that mu is left invariant if and only if Lx mu equals mu. If it's left invariant if and only if Lx mu equals mu for all x. In a similar way, we can define left and right translates of functions on G. If f is a function, an arbitrary function on G, then we define Lxf and Rxf by the following formulas. This is the left translate of f, and this is the right translate of f. And we still have these formulas. Let's denote this formula as star. So we still have this formula now on the space of functions on G. And finally, let's define left and right translates of linear functionals on continuous compactly supported functions. So suppose we have a linear functional on our space. Linear functional. We define functionals Lxi and Rxi on the same space as follows. Lxi is the composition of I and Lx inverse, and Rxi is the composition of I and Rx inverse. So these two maps act on functions, and so we use them. We just compose them with I, and we get two new functionals on the same space. And again, it's easy to show that we still have these formulas now, but now applied to linear functionals. This is a little exercise. Okay, now we'll get the following simple relation between translates of measures and functionals. The following simple proposition. Suppose that mu is a double measure on G, x is a point in G, and I mu is the respective integral. The integral with respect to mu. I claim that the left translate of this functional is nothing but the integration with respect to the left translate of mu. Well, the proof, well, the easiest way to prove this is to prove this equality not on the space of continuous compactly supported functions, but on a much bigger space, namely on the space of bounded Borel functions concentrated on a set of finite measures. Namely, we can easily show this very simple calculation that both functionals agree on the characteristic function of an arbitrary Borel set. For every Borel set B in G. This is a simple calculation. Now we know that every bounded Borel function is can be uniformly approximated by linear combinations of linear combination of such functions. So as a result, we deduce that both functionals agree on every bounded Borel function for every bounded Borel measurable function concentrated on a set of finite measure. But every continuous compactly supported function f satisfies these conditions, so we see that our two functionals are the same. And as a corollary, we see that mu is left invariant if and only if the integral I mu is a left invariant functional. So now our theorem, the theorem which we want to prove, the Harmonic theorem prime, can be stated as follows. If G is a locally compact group, then, first of all, there exists a left invariant linear functional, left invariant positive linear functional, positive linear functional I on the space of continuous compactly supported functions. And moreover, I is not zero. So the existence of such a functional is equivalent to the existence of a higher measure by the previous corollary. And secondly, such a functional is unique up to a multiplicative constant. If I and J are such functionals, then there exists a constant C, a positive constant C, such that J equals Ci. So, by the previous corollary, we see that this theorem is indeed equivalent to the Harmonic Veil result. Okay. So today we discuss the existence of such a functional, and again let's first start by a rough idea. Well, first of all, not with a rough idea, but just first of all we need a simple lemma. number one. Suppose that f and g are two non-negative continuous compactly supported functions on g, such that g is not identically zero. I claim that there exists a positive constant c, and there exist finitely many points x1 to xn in g, such that f is dominated by the sum of the respective translates of g. Well, this is very easy. Since g is not identically zero, we can always find a non-empty open set where g is strictly positive. There is a positive epsilon, and there is an open set u in g, and an empty open set, such that g is strictly bigger than epsilon everywhere on u. And since this f is compactly self-plotted, we can cover the support of f by finitely many translates of u. The support of f can be covered by finitely many translates of u. For some x1, xn in G. And now it's immediate, a simple exercise. It is immediate to show that f is dominated by suitable constant multiplied by this function. So this function will be strictly bigger than epsilon everywhere on the support of f, and that's it. Okay, now let's introduce the following number. If f and g are functions satisfying this condition, continuous compactly supported functions, non-negative functions on g, and g is not identically zero, we define the following number, f g, to be the infimum of finite sums ci from 1 to n, where ci are chosen in such a way that f is dominated by the following sum, ci lxi g, for some points x1 to xn. So what is the geometric meaning of this number? Geometric idea, which is behind the construction. Suppose that we are on the real line, and let's suppose that g is a smooth approximation to a suitable step function of the following form. This is g. And this is f. So let's draw finite and many translates of g multiplied by suitable numbers. So this is the graph of the right-hand side of this formula. It is bigger than f. And we see from this picture that the sum, this is C1 and Cn, this is this number, this sum is something like, this is something like the sum of the areas of these rectangles. So this is an approximation to the integral of f, to the Riemann integral of f, assuming that the integral of g is 1. So in a general case, this number is something like the integral of f over the integral of g, at least on the real line. And again, like in the geometric constructions that we discussed 10 minutes ago, to get a better approximation to this number, we must shrink the support of g. We must take the support of g smaller and smaller. But in this case, again, this number goes to infinity. So to get something reasonable, we must choose a function once and for all, to choose a function whose integral will be declared to be equal to 1. Otherwise, the construction doesn't work. So this leads to the before we do it, let's look at some simple properties of this number. So perhaps it's a good idea to invent a name for this number. Let's call it a relative integral. A relative integral of f with respect to g. Relative integral. So let's look at some simple properties of the relative integral. This is lemma 2. Lemma 2. First of all, the relative integral is additive. It is, I mean not additive, it is homogeneous with respect to multiplication of g by positive constants. Cfg equals c times fg for every non-negative c. And this is clear from the construction. Property 2 is also quite easy. It is sub-additive. You have two functions, f1 and f2. Then we have the following inequality.
То есть первым мы умножаем c на g.
На f. Если бы мы f умножим на c, то но если мы хотим, чтобы cf был бы меньше, чем вот эта штука, если для каких-то цеитых f меньше, чем вот это, то cf меньше, чем c умножить на сумму цеитых. Сумма цеитых умножается на то же самое c. Так что это все нормально. So it is sub-additive. This is also a simple exercise to show that to deduce it from the definition. Property 3 is also quite clear. It is left invariant. Is left invariant. By every x. Property 4 is that if f and g are both non-zero, then this number is greater than or equal to the supremum norm of f divided by the supremum norm of g. And property 5 is a kind of transitivity. If we have three functions f, g, and h, then we have the following submultiplicative inequality. So 4 makes sense if f and g are both non-zero, and here we assume that h and g are non-zero. The proof is a simple exercise which is immediate from the definition of our relative integral. 1 and 3 are absolutely obvious. 2, 4, and 5 are little calculations, but they're quite elementary. Okay, let's now come back to our geometric idea. So as I have already said, to get something reasonable, we must normalize this number by choosing a suitable function whose integral we will declare to be equal to 1. So we'll now introduce some more notation. We choose a function of 0
which is not identically 0. And now, for every function phi, for every non-zero continuous compactly supported, for every non-zero continuous compactly supported function phi on G, we define I phi. This will be a map defined on the space, on the set, on the positive cone of continuous compactly supported functions. We define it by the following formula. By the way, I forgot to say why is it well defined.
It is well defined because of this formula. So formula 4 implies in particular that this number is strictly positive if both f and g are non-zero. Let me mark it here. So 4 implies that the relative integral is strictly positive if both f and g are non-zero. So this is well defined. This is non-zero, and so the whole number is well defined. Let's again look at some properties of this map. Let's call it an approximate integral. So basically, the idea now will be to choose phi such that the support of phi is very small, and then get something which converges in some suitable sense, converges to a left invariant function. So in some sense, this idea corresponds to what we discussed here. In the language of measures. So this is this number in the language of functionals. This number corresponds to this one. Okay. In conclusion, I just state some simple properties of the approximate integral. And the end of the construction will be given at the next lecture. Now, lemma 3. First, the approximate integral is just like the relative integral. It is positive homogeneous. It has the following property. Second, it is subadditive. This is immediate from the subadditivity of the relative integral. It is left invariant. It is left invariant. And finally, property 4 is the following double inequality. This number is less than or equal to the relative integral of f with respect to phi. And on the other hand, it is less than or equal to the relative integral of 1 over the same number, provided that both functions are non-zero. If
f and phi are non-zero. This
can easily be deduced from property 5 here.
Okay, so that's all for today. So the idea of now of the end of the proof, which will be given, the proof will be given at the next lecture, but the idea now is that if we make the support of phi smaller and smaller, then we get a good approximation to a map which is defined on the same set, but which is not just sub-additive, but which is also additive. So once we construct an additive map satisfying these conditions, we can easily extend it to all, not necessarily positive, all continuous compactly supported functions, and we get a left invariant non-zero linear function. So the idea is to make it linear by making phi smaller and smaller.
Okay, so that's all for today. In the next lecture, we complete the proof of the existence and discuss the uniqueness of our measure.